Hi, welcome back to the On Track Whiteboard series. It's Ben Jordan here again with you for part 2 of my RF and microwave PCB design series. I'll just give you a slight disclaimer and say there is so much to this subject that to do it real justice and technical depth, I'd probably need to do 20 videos. We're not going to do that, but what I do want to do is point you to some resources and other things that will help in your journey in learning how to do RF PCB design, things that have helped me, and really just cover the basics so that you feel confident to get started. So in the last episode, what we talked about was really just an introduction to some of the concepts. And I promise that this time around we'll be talking about things like transmission lines and impedance. So I'm going to talk about that, but I do also want to scratch the surface a bit deeper into what I introduced last time in terms of materials, because the materials play a very fundamental role in the performance of any printed circuit board, especially at microwave frequencies. So we'll talk a little bit about that too today. So to get started, let's just do a quick recap of what are the main transmission line types that you're going to encounter particularly doing microwave board layout. And so I've got some cross-sectional views here which I've drawn. Here's some dielectric material with copper traces sandwiched in between reference planes. This is what's called a strip line. Strip line. Most of you know this already, some of you maybe don't, and hopefully I'm filling in some gaps for you if that's the case. Underneath that we have the situation where you have a plane layer, a reference plane, and some PCB dielectric material, usually epoxy resin reinforced with fiber, and signal trace over that on a surface layer and air. So up here we have air, here we have dielectric, here we have copper plane and copper signal trace. This is a microstrip, short for microstrip line. But generally everyone refers to it as a microstrip, right? And then here we have a more typical PCB is a microstrip that's embedded. Strip, let's say it's embedded. What that means is there's no copper reference plane above the trace, the transmission line trace, only beneath it, but there may be additional dielectric material over it. And this is typically what you have as a microstrip on a printed circuit board, where you have a solder mask layer printed over the top. And oftentimes for ultra high speed digital boards and for microwave frequency boards, we typically open up the solder mask and have bare or gold or silver plated copper in air. The gold plating preserves it, prevents it from corroding, which would increase the lossiness of the material. And silver does the same thing. It's not used for conductivity. The conductivity is actually taken care of by the copper because, as I mentioned in the last video, we have this thing called the skin effect. And if I, let me find my eraser here. Let me get rid of some of this crosshatch in here so we can draw some fields and waves. What actually happens, so imagine this is a cross-sectional view looking into or out of the trace. And when we have an electromagnetic coupling of the transmission line, the strip line, the electric field lines go like this. They all couple into the reference plane, right? So the signal energy is densest in this region between the trace and the plane. Most of the energy travels in that space there. It's all about the space, as Dan Beaker would say. And because this is the area where the coupling is, most of the RF and high frequency currents are traveling in the skin effect in this region right here. And the return path currents likewise are mostly traveling in this region of the plane. And because of that, it's actually the bottom surface, a very tiny area of the bottom surface of the conductor that's actually got the electrons moving back and forth at high frequency AC. And so when a printed circuit board is actually manufactured, this area of the copper is typically what's made rough for attachment, as we discussed. And that means this is where we have increased losses. Okay, so that's a microstrip, and we're looking into their strip lines. Are very similar, but they have a much simpler way of looking at it, because with a microstrip, some of the electromagnetic wave is in air, and most of it's in the dielectric. With a strip line, we have coupling, particularly if we have the same distance between those planes. We have coupling to both planes, and so we have a much more uniform electromagnetic wave front traveling transverse to this diagram. So this is what we call TEM, transverse electromagnetic wave propagation, TEM wave. And that's what we have in a strip line. In a microstrip, the signal of interest is still mainly transverse to the direction of propagation of the wave. And so we still often refer to it as this, but it's really quasi-TEM. And that's simply because some of the wave is traveling in the air above the board, and the wave length is different in air than it is in the dielectric in the board, and so the propagation velocity is different as well. So there are different electromagnetic modes in a microstrip, which makes calculating a microstrip impedance and sort of working around that a little more tricky. Okay, so not to get too far ahead of myself, but these are the fundamental types of transmission line you'll be dealing with in a printed circuit board. And if you're wondering how to get an exact strip line which has the same distance on one side as the other, well, typically this is part of a multi-layer stack where your PCB stack-up will have strip line, plane, plane, and you'll have the same distance dielectric here above and below the strip line, and then you'll have some other layers and planes, and you build it up as part of a multi-layer PCB stack. But because the signal doesn't go through the copper, you know, the rest of the PCB stack-up is not part of this strip line structure at all. Okay, now let's talk about some of the behaviors of transmission lines, particularly as it relates to RF and microwave frequencies. Typically in a textbook you'll see a transmission line drawn like this. You know, we have some kind of AC signal source driving a transmission line to some load. The load has particular impedance, ZL, and the transmission line and the source typically have some impedance, ZO or ZO if you're American. And the job of the transmission line is to carry all the energy, or as much of it as possible, from the source to the load. The source may be the output of an amplifier, and the load is probably an antenna to transmit out into the ether, or it could be another chip or whatever. But the job of the transmission line, and this is what you're designing as a PCB designer, is to carry as much of that there as possible with as little loss as possible. And the impedance is is typically characterized, so a transmission line, I'm going to have to erase more here to make room, so please forgive me. Let's just make a little more room here. Okay, so the way of looking at this is there's conductors, and a conductor, a piece of copper like this, which could be a section of trace, has inductance. So when current's flowing in a particular direction, a magnetic field is set up around the trace. When it flows in the other direction, the field reverse. Energy is stored in that field, and it takes time to set up, collapse, and reverse those fields, right? So there's some delay to this, and that delay depends on the dielectric, and it depends on the characteristics of the metal conductor and other materials around it. Also, the transmission line, you know, we know current has to flow in loops, and in a PCB, and particularly at high frequencies, we have a reference plane, which is presumably at 0 volts, and then we apply an AC signal to our transmission line, and it has to, as it travels down the line, it has to charge up the capacitance between the PCB trace and the ground plane, and then it gets to the load, and that energy is transferred to the load like a bucket brigade delay line. So we can characterize or look at a transmission line as a series of infinitesimally small inductors, resistors, and capacitance to the reference plane, and there's going to be some resistance there as well, because that represents losses and other things in these materials, which we've discussed a little bit already. And there's some series resistance which represents losses in the conductor. And so we have this concept of inductance. That's a wonky L, let me do that clearer. Series resistance, capacitance, and conductance, G. So we have this R, L, C, G, and those infinitesimally small sections of circuit join up in series to form a whole transmission line. And that's what gives rise to the characteristic impedance, which is ZO, which is square root of the unit length resistance plus J omega, so there's the frequency component and the unit length inductance, over conductance per unit length, J omega capacitance. Right, so that's kind of esoteric. How do you actually calculate this? Well, some very clever guys over time, like back in the 50s, a chap named Cohn did a lot of research particularly for PCB structures, and using a lot of measurements and empirical data came up with some really good closed fit, curve fit formulas for calculating the impedance of microstrips and strip lines in PCBs very accurately, within a few percent for these types of structures. And others have improved, so Jensen, what are some of the other names? They're all here in this really useful guide, IPC 2252. So basically, all of the impedance calculators you would find, there's a number of free tools out there, and there's impedance calculation built into Altium Designer. They all stem from the work that's been done and distilled into these sorts of documents. And so rather than fill the board full of tons of mathematical equations, I would say check your CAD tool. The PCB layer stack manager in Altium Designer, for example, has an extremely accurate solver for calculating the unit length impedance for any structures and materials you add in. Okay, so having said that, materials play a profoundly important role in how good this transmission line works. I mentioned before the goal of a transmission line is to take energy from the source to the load without loss. There's always going to be some loss. We already talked about the skin effect, and there's surface roughness for the copper. That increases loss, and also the dielectric characteristics increase loss. So what are some of the losses that we're going to encounter? The total loss, usually represented by the alpha, is some combination of conductor losses plus dielectric losses for a strip line. And if you have microstrips where you have some air, you know, you're in quasi-TEM mode, you also have some effective loss added for the fact that there's some radiation. So some of your signal's actually going to go off and propagate into space, just a tiny bit. If you design this right and you have close coupling of the plane and the trace, most of the energy is contained in here, and you don't have to pay too much attention to this if you're not going a long distance, right? But there are radiative losses as well. So how are these sorts of things derived? Let's just look first at dielectric loss, because this is the one that's harder to sort of figure out. I mentioned displacement current in the last episode as well, and that there's a certain finite amount of time it takes to orient the fields in the dielectric material when you apply a voltage to a trace. And some of that energy is lost as heat in the dielectric. So for a strip line, dielectric loss is given in dB per inch typically, and that's going to be according to IPC 2252 and the research that's been done. I don't need to reinvent the wheel here. It's going to be 27.3 times square root of epsilon r times tan del over wavelength. So we can see there's a wavelength, or you know, that's 1 over frequency. So there's a frequency component to loss, and it's inversely proportional to wavelength. The higher the frequency, the more lossy a material is going to be. And this parameter here, tan del, is referred to, people call it the loss tangent. And it's actually something that's measured by the manufacturer of your material and given in the material data sheet. So I have, for example, a standard, this one's from the Gund company, but this is a standard FR4 data sheet. FR4 is the most common material used today in PCBs, and the grade FR4 is actually an NEMA standard, and they all pretty much comply to this exact same characteristics. So for typical FR4, the permittivity, E sub r, epsilon sub r, is measured almost always at only 1 megahertz. So it may be very different. It can be frequency dependent, and in fact it typically is. And look carefully at the data sheet. It may only be given at 1 megahertz like it is on this one. And in this case, the typical values are 4.4. So we have 4.4. Another common value seen is 4.2. And the dissipation factor on the data sheet, it may be called dissipation factor, or D, capital D sub F. That's synonymous with loss tangent. Dissipation factor is loss tangent, tan del. And that's a unitless number. And for typical FR4, the requirement is 0.014. It's a small number because It is actually a tan of an angle between the real and imaginary parts of the epsilon. Not to get caught in the weeds with the math, but that's where it comes from. And so let's take a look at a scenario. Let's look at an example here. We'll come back to impedance in just a bit. Let's say I have FR4 with those characteristics. What's my loss going to be? Let's say, so I run this through an actual calculator, one of the free calculators available that uses the formulas from the IPC 2252 standard, so they're pretty well tested over time and reliable. Okay, so we have a microstrip, let's call it μs to save space. We're at 2.4 gigahertz, so that's right around Bluetooth and Wi-Fi frequencies, which is pretty common these days. We have an impedance of the system and our PCB traces of 50 ohms. So we're using a calculator, using our calculator to determine what the trace width should be for a given dielectric thickness, and that we have epsilon r of 4.1, and our thickness of the dielectric is 4 mils. This is pretty typical for a microstrip. You know, the top layer of the board and the next layer down being the reference ground, and we have 4 mils thickness there. We have a conductor thickness, so that's H. H is 4 mils. The conductor thickness T, which is this thickness here, is 1.4 mils, which is standard 1 ounce copper, which is normal for a surface layer, surface microstrip. Copper, by the way, has a permeability, relative permeability of 1, like most metals that are not magnetic, right? So that means we can ignore the magnetic effects. There's no magnetic effect in copper, but just pay attention to that. Don't use ENIG if you're doing microwave, because nickel on that, just even a tiny thin plating thickness of nickel on that will increase your mu r of the conductor trace, and it will throw your losses and your transmission line ZO calculations way off, because nickel is quite a magnetic metal. So don't use nickel unless you're taking it into account and you can measure things and make sure you're correct. Okay, so what else do we have here? We're going to have a surface roughness of the copper, a pretty typical surface roughness, which is represented by phi of 0.5 mil, say. 0.5 mil. That means the roughness of that surface in root mean square, that the average roughness of that surface where the currents are flowing is 1/2 mil deviation. Okay, so what do we get? This gives us a transmission line with, to get the target 50 ohm impedance, we need a width of 7.398 mil. So about 7.4 mils width. That's the first thing that we synthesize from getting a 50 ohm trace with 4 mil gap there. We need 7.4 mil wide trace. And if this height is increased, the trace, to maintain 50 ohms, the trace will have to get wider and wider. So this is another good reason to at least have a 4-layer PCB with a reference plane on layers 2 and 3, so that you can have good impedance controlled microstrips without having to have excessively wide traces and take up too much space. If you're wanting to have wider traces for higher current carrying capacity because you're going to do something like an RF power amplifier and you need more power, well then you need to increase your dielectric thickness so you can have wider traces but still maintain that 50 ohm impedance. So just bear that in mind. Okay, then what else do we have? We have, and in the next episode I'll talk about the importance of a quarter wavelength more as we start to look at some of the transmission line structures. But a quarter wavelength for this scenario, a quarter wavelength is approximately 736.0280, let's say 03 mils long. So a quarter wavelength is fairly long. That's 736 mils long. That's 3/4 of an inch. It's pretty long. So if you're going to do any RF filters and other structures for 2.4 gigahertz with this setup, you're going to need a reasonable amount of room on the board to fit those things. And calculating all of that with this information about the materials and the resistivity of copper, the surface roughness, and typical FR4 loss tangent tan del of 0.014, the NEMA standard acceptable for FR4. We have a conductive loss, alpha C, of 0.468 approximately decibels per inch. That's what I calculate. And a dielectric loss, so this doesn't seem like much, half a dB per inch. If you're only going an inch on the board, your loss is pretty low. That's not bad. Let's look at dielectric loss. 0.11 roughly, 0.0068 dB per inch. That's all for FR4. That's not too bad. So you can, if you design things right and you've got the room to deal with quarter wavelengths of about 3/4 of an inch, you can do 2.4 gigahertz range microwave board design using FR4. It's okay. It does the job. Now, let's see. If I want to go several inches, or if I'm doing quite a large board, maybe an antenna array, and I need to distribute RF signals to a bunch of different patch antennas, well, now suddenly I'm dealing with transmission lines on the board that may be 10, 12, 15 inches long, and loss becomes a problem. So what do we do then? We use a better material. Okay, so let's look at, I have another data sheet here for Rogers, and various material manufacturers have low loss material specially designed for microwave. This is just one example. So I have a Rogers data sheet here, and what I like about these ones, Rogers add things like their dissipation factor and dielectric constant are tested at the frequencies the material is intended to be used for. So here, dissipation factor tan D, they test it at 10 gigahertz, not 1 megahertz. It's several orders of magnitude higher frequency. So we know this is going to be accurate, and the losses will be even less than predicted down at 2.4 gigahertz. And their dielectric constant is 3 plus or minus 0.04 at 10 gigahertz, 3.07 at 77 gigahertz. So this material has a very stable dielectric constant over the entire intended frequency range of use. So let's redo this scenario. We keep the same characteristics, ZO of 50 ohms. All we're doing is changing the material. So epsilon R is 3. Maybe I should do a different color here, just so we see the contrast. 3.07. All the dimensions stay the same. The copper surface roughness stays the same. tan D is the other thing that changes. So instead of 0.014, it is now 0.0011. So more than an order of magnitude smaller loss is going to be experienced in this material. And so we've gone from 0.468 dB per inch and 0.11 dB per inch for conductive and dielectric losses. Now let's have a look. Let's have a look what happens. We rerun the numbers. Now the width of the trace for this same material, thickness but different dielectric constant, is now 9.1 mils. So the width actually increased. We need a wider trace because of the lower E sub r. So the lower E sub r goes, the wider your trace is. So to get a 50 ohm trace with E sub r of 1, which is air or vacuum, you need a much wider trace. This is also typically why, you know, antennas have a higher, air-based antennas have a higher impedance than 50 ohms, and we need to have balance and things to match them. What else? A quarter wavelength at this frequency is 817.4-ish mils. So our quarter wavelength, the size of our features, things like stubs and filters, they're all increasing. So we need more room. So that's maybe a downside of also having a lower E sub r, is we increase the length of our features and the width for the same system impedance and same frequency. And then, but then look at our losses. Instead of the conductive loss actually lowers because the conductive loss is affected by the material in the dielectric as well. Conductive losses are, they depend on the frequency of operation, the conductive characteristics of the copper, but they also depend on ratios, you know, and the size, because our for the same impedance, because this changed, the width got wider, and so the conductive losses drop. The conductive loss goes down because we get a wider trace. Okay, so conductive loss here is now a little bit less at 0.392-ish dB per inch. But really where there's a huge difference is the dielectric loss. Instead of 0.11 dB per inch, we're now down to 0.0076-ish dB per inch. That's I'm rounding numbers here. So it's 2 orders of magnitude in dB at least, lower losses for using a material that's specially made for RF and microwave. So if you're only doing small boards with a little bit of Wi-Fi antenna or some small features, and most of your work is being done on chip, or you have a module mounted on the board instead of doing chip down, then FR4 is totally fine. But if you need to do some huge antenna array or some board with a lot of mixers or directional couplers or splitters and combiners on a board, then your losses are going to become a problem because your feature sizes are so much bigger, and you need to pay attention to that. So in that case, use a good low loss material. It will cost more, but your product will perform, and that's the only way to get in spec sometimes. So that's just 2 examples of what we do to calculate the impedance and then figure out what kind of material we want to use. There's some other neat things we can do with impedance, but one of the most common things that's going to happen on a board is that we have different impedances. And so very quickly, and this will be the end of this episode, When looking at a diagram of the actual copper features, we typically see them like this, just as you know, a strip. And the textbooks will look like this. Now, I've actually seen YouTube videos where people getting into this for the first time didn't realize that that's not just your piece of copper, but there's actually plain layer underneath it. Like, if we're looking into the structure on the edge of the board here, in this case we're looking down from on top. And so we take for granted that there's a copper plane underneath that as your reference plane. The only time your copper plane is removed is when you want an antenna and you're intentionally causing these fields to radiate out. And that's another episode towards the end of this series. So we're looking down on top, and we may have a chunk of copper like this, that maybe it's a certain length, L, and somewhere up here we have a pin of an IC which is transmitting, it's a source, it's sending data in the form of RF energy into this trace. It's maybe a 2.4 gigahertz wave going into this trace, and then somewhere down here, down the line, we come to a much higher impedance trace that's narrow. Maybe we have to neck it down to fit in between two pins or something. Well, this here is an impedance anomaly, and we know what happens when we create a transmission line of one characteristic impedance. Let's say that ZO is 50 ohms, and then here we have a narrower trace. Maybe that ZO of that one is 100 ohms. What happens? Well, half that energy is going to encounter this transition and bounce back up the other end. If you transmit into an open circuit, all the energy goes back. If you go into a short circuit, let's say that's a dead short to ground, all the energy goes back but negative voltage, or inverted voltage. And for going back to your basic transmission line theory, you know that that's what's going to happen. So what do you do when you need to change transmission line impedance from one to another? You have to use what's called a quarter wave transformer. And the easiest way to do that is, you know what, from the calculator, you know how long a quarter wavelength is. Before we had a quarter wavelength of, let's say, quarter wave in our scenario is 768 mils. Okay, so what do? We have one transmission line here, and we have another one here, and we need to join them. Well, we taper, we put a tapered segment in. This is the simplest way to do it. And that length of that tapered segment is 1/4 wavelength long. Maybe you don't have room for that, and can you tolerate the reflections if it's got to be shorter? Well, you know, as a circuit designer, you have to know that. But generally what we do is we insert this tapered section, and that gives a gradual transition from one impedance to another, and pretty much eliminates any reflections if you do it that way. There are even better scenarios, and there are calculators you can find at Microwaves 101, where instead of having a hard taper like that, they've found an even more optimal approach is to have a polynomial curve. It's a very slight curve. You can almost not see it in the final design, but there's an Excel spreadsheet you can download from there that will allow you to calculate the characteristics of that curve based on your target, and that gives zero reflection back to the source, which is good. That's a good thing. You want all your energy to go to the load. And this has been pretty long, this one, and there's a lot more we could look at, but I feel like in the essence or in the interest of not going too long, we should probably finish this episode here. and look forward to episode number 3. I hope this has been useful. We're going to do more in episode 3. It's going to be looking at what are some of the other things we do with these shapes at a quarter wavelength. We're going to talk about stubs. We're going to talk about a few different types of stubs. Again, not diving into the laborious math, because the goal here isn't to give you a huge math lesson, but to point you towards some resources that will help. And again, most of the time all you need to know is those essential characteristic impedance and transmission line characteristics of what type of line you're doing, and the calculator will give you that. And from there we know a quarter wavelength, and you can do some other cool things with quarter wavelength sections. So until next time, I hope that's useful. If you like it, give us a thumbs up. If you have any questions or comments or things that you would like me to discuss in a future episode, please comment below and share with your friends, your colleagues, and subscribe so that we'll let you know when the next episode is on its way. You'll get a notification. Thank you for watching. It's Ben Jordan, and this is the On Track Whiteboard series.